Our final project is on city traversal optimization. First, I'm going to give you some background information on genetic algorithms, which is the main idea behind our program. Then, Don's going to talk about the problem we're trying to solve and how we're solving it. And finally, Aldrin will finish up by demonstrating the program itself. So, genetic algorithms are experience-based techniques for problem solving. Instead of trial and error exhaustive searches, this method speeds up the process of finding a solution by using readily accessible information to control problem solving. So we're going to use giraffes for our example of genetic algorithms. So first, you start with initial population, and it is with randomly generated states. So giraffes used to have randomly sized necks, so they were all very neat in size. Next, the fitness function produces the next generation of states. So it gives a score to each state depending on how well each state satisfies the problem solution. So since giraffes live in Africa, where the soil is very sparse, or the grass, they're forced to resort to eating from trees. The problem in this case is being able to get food from the trees. And so most of them actually have a very hard time of doing this, and so they will have a lower fitness score. So the next step is selection, which chooses pairs that are most likely to reproduce based on the fitness function. So each generation produces mutations, which changes the fitness score. Some are not very useful, but sometimes one comes along that actually is better at solving the problem. So the short ones are less likely to reproduce because of their inability to feed, and this results in the taller ones have a higher probability of reproducing. And so the next generation will have a lot more tall ones than short ones. This is very important because the generations produce different mutations that could solve the problem better. So this is something we'd really like to emphasize. So since they all result in a higher fitness function and higher probability to reproduce, each generation will be an improvement on the previous one.
Consider a simple city laid out in a grid with streets placed at regular intervals. There might be parks, apartments, busy streets, businesses, a bridge, etc. Now imagine that you, the driver, urgently need to get to the bank on the other side of the city to make a deposit, and you would like to find the fastest way to get there. The problem is, some or most of the intersections have stoplights, so the fastest path turns out to not be at all obvious. You could use a simulation to check all the paths, except that the number of paths increases really fast with the size of the grid. In fact, for just considering monotonic paths, so no loops, no going backwards, the number of paths you would have to check increases as 2n choose n, which is actually faster than exponentially. This is where algorithms come in. A conventional optimization algorithm might start by guessing at the fastest path, and then making iterative adjustments until it finds a local minimum. Because for this problem, the time cost associated with each step is coupled to every step before it, the solution space is gigantic, containing multiple local minima, etc. So the conventional methods fail. Really, you need to be able to explore the parameter space completely. And to do that, we use a genetic algorithm composed of trials and generations. After each generation, the fastest path is determined and recorded, and then the program makes it more likely in future generations to go to that part of the city. At the end of the day, the fastest overall path is reflected in the fastest path of the final generation.
We've taken these ideas and implemented it into a program to simulate a car running multiple trials through a city over multiple generations. The left side of our user interface represents the parameters of the simulation. The user can specify the size of the city, the number of stoplights, the frequency the stoplights change, the starting and ending locations in the city, as well as the number of generations and trials per generation. We can also choose the type of algorithm the car will move through the city by. Angle minimization chooses to minimize the angle between the car's current direction and the end location at each intersection. Weighted probability moves towards the goal 90% of the time, and randomly the other 10% of the time, representing a mutation. Or you can choose to move randomly every time at each intersection. First we'll try angle minimization, and I'll click start. We can see the stoplights changing red and green at each trial, and white represents no stoplight at that intersection. Second, we'll look at the probability weights. This represents the optimal path at the end of each generation. These weights increase the probability of a car traveling to a particular intersection for each succeeding generation. The darker the box, the higher the weight. Finally, we can see the fastest time at the end of each generation on this table on the side. At the end of this simulation, we can then visualize the optimal path the genetic algorithm is. With sufficient trials, the fastest path should drop in duration for each generation. When plotting times from a sample of 20,000 generations, we can see that in fact the majority of times are getting quicker, not slower. If we choose to use the weighted probability algorithm, we can see this other path straying from the optimal path, which almost represents the 10% genetic mutation between each generation. If we use the random movement algorithm, we see that there is almost no pattern to the weights. Genetic algorithms such as these have endless applications, such as use in the real world, like in GPS systems, for city planners, or even for modeling natural situations like water runoff from mountains.